You have homework from GR, and I'm going to send you to homework 2 from. Yeah, there is an overlap, but you won't have to start this weekend, especially that I think you will be able really to do calculation with what we are going to see on Monday. So it's just for you to read it and have an idea of how long it is, and you can organize yourself, this kind of thing. But yeah, you're going to have some overlap. Usually each class is going to be each time 2 classes at the same time, which 3 homeworks. So it's going to be, you have to get used to that. Okay, great. So now we're going to finally start talking about path integral. So I'm just going to talk about that in the quantum mechanics framework and not quantum field theory, okay? You will see quantum field theory in the next block of class, and so I'm not going to start. But I think we can still develop the techniques, and it's going to, many of the calculations we're going to do are going to be similar in quantum field theory, okay? So the first part, we're going to consider, so this is what we defined. So it was introduced in the tutorial yesterday, this object, so which are just the matrix element of the time evolution operator in the position basis at what are called the propagator, or sometimes it's also called the Green's function, depending on what you're calculating. But I'm mostly going to use the term propagator. So. And so first we're going to look at, we're first going to describe a kind of general strategy that is going to lead to the representation of this matrix element in terms of path integral, okay? So let's start from the position 1 function in the Schrödinger picture. So now I'm going to work in the Schrödinger picture, and I'm going to look at a wave function, which by definition and now I can say that this can be seen as a time evolved vector using from a previous time t prime and now if I introduce a decomposition of the identity here, okay, in terms of, so here, so it's x second, what I'm going to get is I can make the propagator appear here. Right. Okay. And this, of course, is just so the wave function at the point x prime. And here is what I call the propagator. And so, what does it mean here? This means that the time evolution of a vector, okay, so the time evolution of this vector, normally you use that it's in terms of this, so in terms of abstract vector, you use just the time evolution operator here, and now it can really be seen as the propagation of an amplitude in configuration space, okay? Where now this is called, as I said, the propagator from this initial point, space-time point, to the finite point x prime prime t prime prime. And so just an interpretation here, if you now look at, and we're going to come back on that later. Sorry, so x prime t prime squared, so the norm squared of this object. Of course, this can be interpreted as the probability up to some proportionality factor of finding the system at the point x prime prime at t prime prime if the initial if at initial time t prime the system was in x prime, okay? Okay, so this is just the standard interpretation of that. So now the idea is going to find a way to compute this object for very general potential, okay, where the h here, the potential can be quite general, and kind of general method. So for practical reason, I'm going here to go to pure imaginary time. Okay, so do you know how this is called when you do that? Okay, yeah. So here I'm going to do that because then I'm going to be able to compute everything just using Gaussian integral and this kind of thing. So in the tutorial this afternoon, you're going to redo more or less a kind of similar calculation that I'm going to do now without doing the weak rotation. So this means that then you will have to deal with complex integral and do some contour integrals, okay? So here I'm going to avoid that, so and I'm going to do some weak rotation, which also allow to make some a link with maybe what you're going to see also next block with in statistical mechanics, where so now the weak rotation, this means that I'm going to go to pure imaginary time. And so now instead of f of t, I'm going to look at a function g of tau, which is defined as where tau here is of course a real number. And so if we apply that to the time evolution operator here, sorry, I already get that. So in particular, we're going to work first with time-independent Hamiltonian. So in this case, you're going to, sorry, let's rewrite this. So if I apply this to, and so here it's going to be an exponential of -1 over h bar and in fact, if you're familiar already with statistical mechanics, an operator of the form where it's exponential minus usually you will have a beta h, then is going to be called the statistical operator, which is the density matrix at thermal equilibrium, okay, as you will see. But okay, so this you will see that in, so here it's more for practical reason to do calculations that I'm doing that, and you will see what this change if you don't do that in the tutorial this afternoon. Okay, so let's now present the strategy we're going to use. So so the idea is to use a time-independent Hamiltonian. So we are in the Schrödinger picture. So usually it's going to be of this form, where, for example, of course, the x could be just x squared when in the case of the harmonic oscillator, but we see that then the idea of next week is going to go to the perturbation theory. So usually we will have some a typical example then would be to study something like where you have a x term, but then you have also a quadratic term with a lambda, where lambda is going to be much smaller than the alpha, and then do some perturbation. Okay, so this will be kind of a typical example that we we will consider. But now let's find a way to compute this U valid for any V, okay, any potential. So let's focus now on the matrix element, okay? So this means on this, with the propagator, okay? And so I'm going to forget about all the indices very soon. So this means that we want to look at this kind of object, okay? And so what is the idea now? Is that here H is time independent, okay? So H with H, of course, is the commutator of the H with H is 0. So what I can do now is look at this propagator as a propagator on a smaller time interval times another time interval, okay? So I'm just going to do first this kind of, to give you an idea of what we want to do. So I'm going to do this first decomposition. So here from and -2. Okay, and this I can do it because of H is time independent here. So I'm separating the time evolution into two smaller ones. And now let's introduce between these two. I'm going to introduce the identity resolution. So I know that some of you are familiar with the path integral formalism. I've seen that in the survey, but it's not exactly the case for everyone. So I still want to present this general method, which is anyway useful to have seen at least once. So, and so you see that here, this just means that I'm looking at, so I forget about the time here. And so this is a kind of quantum mechanical rule for when you have two different, how you combine amplitudes, okay? But so what does it mean? How you interpret this? You know that a particle propagating from x prime to x prime prime must be somewhere at an intermediate time tau, okay? And labeling that intermediate position by x here, you see that you can compute the amplitude, the total amplitude via this position x, okay? Where x could be the position where the particle is at time tau. And then you will what you do here is that you integrate over all possibility, okay? Because as we said, so we just know that at initial position, at initial time, the particle is here. At finite time, particle is here. At any time between these two, initial and final, it should be somewhere that we label by x, and this can be any position. So now, this is a bit the idea of we're going to use. And now we are going to decompose this time interval into n subinterval. Okay, so here I just look at one case, but so let's now divide. So now we want to do that in a more generic case. So we want to divide the time interval in n equal subinterval. Okay, so I start from, I'm going to call tau 0 tau prime, okay, and then tau n is going to be tau prime plus n time an epsilon, where epsilon here is the subinterval. So it's the final time minus the original the initial time divided by the number of subinterval I have. And of course, I need to specify what is the last one. I want that the last one is. And so for this now, this means that I can do the same trick here. Instead of dividing my time evolution operator into 2, okay, I'm going to divide into a product of n, okay? And so this means that now can be really written as the product of n and I'm going to use now the same trick, so to compute my propagator, in between each of my small time evolution operator, I'm going to insert a resolution of identity, sorry. So let's just see what you get now. So you just get that K is equal to a product, now inserting identity resolution. What do we get? We get that now we're going to get a product. So we're going to see how many we need to have here. And -1, xi minus 1. And then I'm going to start at I is equal to 1 to n minus 1. So then I need to add the last one, which is x . Okay, so I did exactly the same thing that I did before, decomposing this time evolution operator into very small time evolution as a product of very small time evolution operator, meaning on a very small time interval. And then, so here, of course, you could write that indeed it's also a product of very small propagator, okay, where you're integrating over all. So here, epsilon is the time duration of each interval. And so here, what is important is that the tau n, the small tau n are fixed, okay? And you're integrating on all intermediate x, small n or xi as you want, corresponding to each tau I. So let's maybe draw a picture of what this means. So here, what do we have now? So let's say that this is x in terms of tau. So for simplicity, for the drawing, I'm just going to say that tau primes, meaning tau 0 is 0. Okay, so I'm starting here. Then I'm dividing this in interval of duration epsilon. Okay, and then at the end, I end up at tau second. And then, so I'm starting at tau 0, I have my x0, which is x prime. And then, so this tau here are fixed, but I'm going to integrate over all possible xi for a given tau I. Okay, so for tau 1, for example, I can have any option where here it's the x1, and then from here I go on to and then you have this kind of picture for all interval, and you end up at again so here this amplitude here now, or the propagator if you want, can be seen as a sum over all these n-legged paths. Okay, so here Now this means that the propagator, we have written as a sum over all n-legged okay, and this is just this previous. And the idea is that then we're going to take the limit n goes to infinity, okay? So when then the number of toes are going to become infinite, and this means that we can interpret this as summing over all possible paths, okay? Where we consider that now, so when n goes to infinity, then it's like summing over all possible paths, where we're going to consider that path x of tau, where tau now take any value between. And where, of course, these paths are going to be continuous but not differentiable, okay? But so now let's focus on one propagator for one sub-interval, okay? And see what we can, if we can write that explicitly. Okay, any question now? Yeah.
Is that a big N? Are the taus big N's at the last propagator in that integral?
So is it over there you're asking me? Oh, yeah. Here? Yeah, thanks. So, of course, we are on the last subinterval from here. So, here to here, and indeed it's from 2n to 2n minus 1. Okay, thanks.
I have a question.
Yeah.
When you do this big rotation, your evolution operator goes from being a bounded operator to being a non-bounded operator. Is that a problem?
So we're going to, so you're right here, but in fact, all the quantity we're going to compute, so you're going to see that first, if we just compute this object, even in without the weak rotation, it's divergent, okay? Because we're going to see that what is going to appear as a measure is going to be divergent. So the way we deal with that to get finite quantity is that then we divide by, so we're going to see that each time, so the divergence, what's come in the divergence only depend on, in fact, the free case, okay? The free particle case. So we're going all the ways to divide by the free case, or a case that we know, in order to, a reference case that in order to remove the divergence, okay? So here, since we are looking at, even if it's unbounded, since we are looking at the matrix element, it's going to be, at the end, it's going to be fine, okay?
Can't we just say that it's also bound as well, because we're always propagating forward in time, so T2 bar is always going to be larger than T.
Yeah.
So it's bound by 1.
Well, yeah, but you can also consider the one that is where T prime is.
Yeah, but that's true that also here I'm more or less assuming, because I'm doing this kind of decomposition here, I'm assuming that I'm considering T prime smaller than T second to do the...
So you need to put like a temporal order.
Yeah.
What's the motivation for introducing the weak rotation here? I mean, why are we doing this? I still don't see it quite clear.
Yeah, so you're going to see that. So right now you don't see it because I haven't done any explicit calculation.
Okay.
But then I'm going to do some explicit calculation, and in fact we're going to deal with just Gaussian integral, which are real. And you're going to see in the tutorial you're not going to do that, and you're going to have to do some complex integral with contour integration and this kind of stuff. Okay? And Also, you will see that when we talk about the partition function, in fact, it's a way to write, it's always defined in using the weak rotation. So some of the objects are always defined using the weak rotation and then related. But in terms of calculations that we're going to perform now, you're going to see that I'm just going to deal with Gaussian integral. Doesn't mean that it's completely easy, but it's not. It's easier. That's what you're going to to do at some point. But not. In fact, it's not so much different. Once you know one value of a given complex integral, then it's going to be what it is. Okay, so now let's focus on one subinterval. So maybe I can still start from here. So I want to propagator and let's first look at the case, so meaning something which is inside the bracket above. Let's, in fact, first focus at the case v is equal to 0. And in fact, in this case, we can do it exactly, and it's the calculation you're going to do also in the tutorial. And even you can, so in the tutorial, you're not going to look at a subinterval, meaning at a very small interval. You can really do it for any interval. So here, since I'm interested in the expression, I'm just going to keep this this notation, but it's not really important. So what I want to compute here is something like this, epsilon. Okay, so the epsilon here is really not important. It could be a large t. It's going to be the same. And okay, so this is my what I'm going to call U0 of between okay, and the epsilon comes from that. The difference between the two, just give me epsilon. Okay, so now I'm going to use what we have seen yesterday, meaning I'm going to introduce insert resolution of identity, but now using the P eigenvector. And so this can be written now as minus epsilon. Okay, so what do I get here? So first, what do I get from this term?
E to the minus c epsilon, whatever, and p squared.
P squared, and then, yeah.
And
Okay, where now there is no hat anymore, meaning it's the eigenvalue of P, okay? And so now this means that if I recombine with everything, what I get here is now this object and so we have seen the value of this yesterday, so this wave function, how to write that. So what is the final result here? So I get the minus epsilon p squared and
H bar xp.
yeah. So what is the sign now?
Xn minus xn.
Yeah. Okay, and I'm missing a normalization factor. Okay, very good. So what does it mean here? This means that this is the Fourier transform of this object, okay? So you get exactly the result. If you want to do, so in the tutorial, you will see another way to compute it, where here you won't get this Gaussian, okay? You will get with a minus, and then you will compute that a bit differently. But so here, I'm just really going to use the fact that here we get the Fourier transform of a Gaussian, and use directly the result, okay? And so I just get that the xn for the free propagator between x n minus 1 is just given by, so yeah, you get this factor coming from the fact that your Gaussian is normalized. Okay, so here I more or less use this short way of going from here to here, but again, in the tutorial, you're going to do that explicitly using a different way because you don't have the weak rotation, and then you will compute all the term in using an iterative method. Okay, so let's. Okay, so this is the result for the free case, and we're going to see that in fact we're going to use it often. Okay. So now let's look at v different from 0. So now for v different from 0, we're going to use the fact that we decompose this into a product of propagator on a very small time interval. Okay, and so we're going to use a kind of expansion using the fact that this is very small. So now we have that delta. We're going to use that. So it's very small. So we can expand this k, which is given so by xn. So this is an exponential of h. So it's going. The first term is going to be the identity. So the identity then it's xn with xn minus 1. So this is just a delta function. And then the second term is going to be, so we have a minus epsilon divided by h squared. And then we need to figure out what is this object. So let's now just consider, as we said, h of the form and use more or less the same trick as before. So now just focusing on this part. Okay, what can I get? So I got xn and let's introduce directly a deletion on the identity. Okay, so here it's like exactly like before, so you just get a p squared. So here it's still an operator now. P squared over 2m, and then for this term, we can see that, so it's Hermitian, so it can also act on the xn. So what do we get here is just dp p squared v of xn. And then I'm just going to get the same exponential as before. So a, which was ip xn divided by my normalization factor.
Sorry, could you explain where you got that expression for k?
So sorry, which one?
The expression for k for v not equal 0.
Okay, so this is not, yeah, sorry, maybe it's not the total k, so it's more, it's the k from okay, so it's on the sub-interval. Okay, so I'm just using, looking at one of these terms. So now u is the exponential of, okay, so what you want me to write is maybe what?
I think I got it, yeah.
Okay, so yeah, u is just exponential of minus t tau n minus 1 divided by h bar times h. And now this tau n minus 1 is just the epsilon. Okay, so this comes from, yeah, so maybe I can just write that the u here is just exponential minus epsilon. Okay, and then it's really just an expansion at the first order in epsilon. And now I'm looking at this particular evolution. Okay, so so now we can deduce this was just this term. Okay, so now we can plug everything into the k for the subinterval, and so which is xn u n minus 1, and we can rewrite this as an exponential with, if we don't forget that it's up to term in epsilon square. Okay, so this can be rewritten as h bar of xn minus xn minus 1. So this is this term. And I'm going to say that this term is epsilon of p squared okay, so everyone can see it's not too okay, we're almost there. So now what can I say here? So here I'm integrating over p, and what is the term? What are the terms that where I have a dependence on p here? So I have this one, and I have this one because the v can be put outside, in fact, of my integral. And what do you recognize here between this product of two?
A Gaussian.
Sorry?
It's a Gaussian. Well, it can be turned.
Yeah, and which Gaussian is that?
Saddle point approximation.
It's just the one we had before, if you look at the term, okay? It's the one for the free. So we have this Gaussian, and again, it's going to be the Fourier transform of this Gaussian, which is exactly the same thing that we have for the free case. Okay, so this means that all this integral with the normalization here is in fact the free case. So what does it mean? This means that we can really use what we just computed before.
Sorry, I'm not clear how you got the last line.
Okay. I started from this propagator on the subinterval. Okay. So is that clear that this u is in fact exponential minus epsilon divided by h bar times h? Okay. Where now I expand that. And then the second line was computing that in the specific case where I consider h of this form. Okay, an Hamiltonian of this form. Where, so then I get this expression. And now I'm using this expression to plug it in here, okay? But the point is that you can, in fact, rewrite. So, okay, maybe I should add another line. But so, or if you prefer, if now you expand this, okay, at the first order, what you're going to get is just the exponential, the integral of this term times 1, which is exactly going to give you a delta in x minus x1. And then the second term is going to be minus epsilon h bar p squared over 2m plus v. And I'm looking only at this term. So it's exactly the second term. Okay? So here what I'm using is that indeed to go from, if you want to expand that to go back to the original result, what you need to remember is that indeed dp of exponential is just the Fourier on form of 1, which is a delta function. Okay, this is. And why am I interested in writing this way? It's because now everything is as an exponential, and I can recognize this term times this term. This is independent of p, so I can put it outside my integration, because the integration is just over p. So this means that what I'm computing here is just exactly what we just did for when v equal to 0. Okay, so now what is the result that we get?
Without them telling us.
Is that for a subinterval, this object, the propagator for a subinterval, is in fact, so now I'm using the result of the free particle that I just compute. Okay, so this is just what I get from h bar epsilon. I think I have an m here, minus m, minus epsilon over h bar of v of xn, plus okay, so here I just used this result. So all the term in pink here or red, I don't know, can be with the integration over p can be combined to give exactly this term. And then I'm just left with the purple term, which is an exponential, of vxn times this epsilon over h bar. Okay, so this is exactly what. Okay, you still there? You okay? Great. So now this is a term from one subinterval, and we have n factors in the amplitude. Okay, so now we can combine. So now we are going to combine what do we get? We get the propagator from the initial point x prime tau prime to the final point x prime prime tau prime prime, which is, so again, defined as a matrix element of the time evolution operator. And we combine them, and as I said, what we want to take at the end is take the limit n goes to infinity. So we're going to be interested in doing. So now I'm going to have m times this factor. And I have a product from if I go back to this one, so from I is equal 1 to n minus 1 of the xn where let me give you what is this. So it's not only depend on x, it's also depend on this epsilon, and it's a discrete so, and the subscript E is for Euclidean, because since we did this weak rotation, we end up with a kind what we call the Euclidean action. K is equal to 1 n, and then so I have a square. So this is just this term. Sorry, the epsilon is here. So the h is already factorized, okay? And then I have a, what is the sign? Yeah, so minus, so I have a plus v of xn. And this, the relative sign between the kinematic term and the potential come from that, yeah, we did this weak rotation, and so this is what we call the Euclidean action, where we have this difference of, so it's not yet exactly the Euclidean action because we haven't taken the limit epsilon goes to 0 yet. But so then the idea is that now we can factorize by epsilon. So I'm going to get some epsilon coming out, and this is going to be divided by epsilon. Yeah, I'm missing one epsilon here. Yeah, good. Okay. So now, yeah, let's say it again. So if I factorize by epsilon here and take now the limit epsilon goes to 0, you're going to see that this is going to be the derivative of x squared, and I'm going to get v, and this sum is going to can be seen as an integral. Okay, so now factorizing by epsilon, and then taking the limit epsilon goes to 0, we get really now what we call the Euclidean action. Okay, so before it was more a kind of discrete version. Where now from 2 prime where square plus v of x of 2, And this is the way we So where here the paths are going to be continuous but not differentiable. And this is what we call the Euclidean action associated with the Hamiltonian. And again, you see that the difference with the Lagrangian. Okay, Euclidean Lagrangian. The difference comes from the sign here. Okay, so just we're almost there. So now we can take this kind of formal limit of, so what is the important expression here? So the important one is really this one, okay? And then the limit that we are taking is more formal. So for some calculation, at least for the first calculation, we are going to, okay, so this is, and the expression of what we call really the path integral is obtained when we take this formal limit n goes to infinity and epsilon go to 0 in this expression. And then where we write, so taking of this expression, we get we can rewrite this like this. So let me explain all the term in a second.
Are we supposed to divide by another epsilon before we take the limit or something?
In here?
No, I mean, so if we look at the first one, first of all, we don't get the second derivative. Second of all, the limit, like if we take epsilon goes to 0, our v is going to be not in the final limit, so.
No, so you factorize by epsilon. So then you get epsilon with the measure, with the sum, and then you get no epsilon here, and epsilon squared here. So then it's really the, and this really, when you take the limit, give you the integral term. Okay, so you need to factorize by this epsilon. Okay, so I wrote it here. I didn't write the next step, but it's like okay. Thanks. Okay, so me write this formal expression, and then give you a few comments on that, on the meaning of this expression. And where, oh, okay, don't write. So this is what is called so here it's the configuration. We can also get a phase space path integral where it's just that we could have done that before. Instead of solving the P, we could have kept them and then where now the S of E is given by this expression. Okay? So, few remarks here. So first, this integration here is viewed over all function q of t, x of t, tau, sorry, x of tau, that as you have this boundary condition, okay, satisfying with that, and this gives you kind of the weight. Now, a few words about the measure term, okay, so this one, this notation, it's going to denote the integration measure for the path integral, and it has to be distinguished from just a normal integral, okay? And in fact, to do explicit calculation, we're going to see that at least, so of course, it won't be very, this new framework won't be very interesting if for all calculation, you really need to go back to this not so nice formula, okay? But to compute the first one, meaning the So for example, we have computed here the free particle case, but we can do it again using now the path integral formalism, and we're going to see that we get the same thing. But then usually for more complicated case, we're going to be interested in either a perturbation, so we won't come back directly to that, and we're going to develop maybe not today because it's already late, but on Monday, few techniques depending on the form of your potential that can be applied, and where of course you don't have to go back all the time to this expression. But just what I want to say is that the way you really want to understand, this is quite formal, this limit. So rigorously, if you want to understand this expression, it's really given in terms of this one, okay, right now. Yeah, so also in this symbol, what is hidden here is this term, okay, where you see that when n is going to go to infinity, is of course going to diverge. And so that's why usually we're going to see that when we compute quantity in path integral, we are going to normalize by dividing by your reference path integral, where you know the value. So for example, for us, we're going to compute now, or we know already, but we're going to redo using that the free case particle, the free motion path integral. So then usually when we're going to compute, for example, the case of just the harmonic oscillator to have something non-divergent, we're going to divide by the free particle case, okay? Last remark before taking any question is that, of course, here you can easily go back to the action, the classical action, if you just perform a inverse weak rotation, okay? And then, of course, you will get the same expression, but here, now what you get is really the action. Oh, I erased one part. Where with the correct sign here, okay? Okay, so any question right now? Yeah.
Where did the factor of m over 2 pi h bar epsilon go?
This one? So this one is hidden in the measure here, okay? That's what defined. It's really a measure term. We're going to see that in a moment. And again, also we also have this kind of, here if you really be careful, you have this plus, 2 of epsilon squared, and here you should have it at kind of power n, but when you take the limit, it goes to 1, okay? So this, the 1 plus this term to the power, so we forget about it, okay? But there are some subtleties. And so really, the safe case is to really start from that when you're not sure what to do, okay? So now, we already computed this free propagator, the free particle propagator, because here, as I said, instead of epsilon, it could be t, where t is the difference between tau prime prime and tau prime, and you will get the same result, replacing just epsilon by big T. But this has been computing using just canonical quantization tools, okay? We haven't used the path integral tool. So now let's try to compute this, again, using the path integral, okay? Meaning we want to use this expression and see if we recover what we should. So any questions first? Yeah, I already asked. Do you want to, you need a break, but it's only 30 minutes left. Yeah, sorry, I was thinking to be much faster because in fact I'm not even at half of what I was planning to do. So am I too slow or? Okay, so I don't know why, because the first 2 lectures I was really exactly on time on what I planned, and today I'm like completely half of. Okay, so well, let me know if it's, I can try to go faster, but the point is that, yeah. And have you already seen this derivation? Or? So yeah, some yes, some no. Okay. So at least for the no, it's useful. Hopefully for the yes, it's also a good to refresh. And you're going to use it again in the tutorial this afternoon. So hopefully at the end of the day, you're going to be very like.
Maite, could you put the notes on the wiki before the tutorial today so I can see the maths in?
Yeah. Okay. Yeah. I can do that for. That's good that I'm late because the second part of the lecture, my lecture notes are a bit like incomplete, I would say. But okay. But for this part, I can sure put them as soon as I leave the room. Yeah, I know that some of you are asking for to get lecture notes before the lecture, but the point is that, so it's the first, as I said, it's a new course, so it's the first time we're doing it, and I'm still working on the lecture notes usually very right before the lecture, which is not so good, but yeah, it's a reality here. So yeah, sorry about that. Free particle. So you know the result, okay? Because it's okay. Oh. So is it like? Okay, so it's here, but unfortunately this one is not moving, so you won't see it. But we want to recover that, okay? And since I also want to keep this expression, I cannot use this blackboard, so yeah, you have to remember. Okay, so let's start by using this expression in the case of a free particle. So this term does not depend on the action, okay, so it's always the same. So I'm going to get and now I can express explicitly my kind of discrete action, which is the sum from k equal 1 to n of m over 2. So I only have this kinematical term. Okay, so again, you're going to do that in the tutorial also. So I'm going to expand give you some of the steps, but then anyway, it's always better to do this kind of calculation by yourself explicitly. Otherwise, so here's the idea. Even if in the tutorial again you're going to get something with a I, whereas here, in fact, it's just some Gaussian integral. The only difficulty is that all these Gaussian integrals are coupled, okay? But you're going to see that in the tutorial you can really do that by an iterative method, okay? So you're going to prove it that it's true for n equal 1 or 2, and then or 3, maybe because otherwise it's trivial, and then prove that by iteration. But here, so I'm just going to expand that to show you that it's indeed Gaussian that are coupled and give you the result. So just to give you an idea of how this calculation can be done. So here we get have all these terms until x2 minus x1 squared x1 times this m over 2 epsilon. Okay, where x0 and xn here are the original point. So x0 is x prime and xn is x prime prime. So this is just some Gaussian integral to compute. You're going to do that really explicitly in the tutorial. So here I give you what you get. Then we're going to see. So you're going to get, you still have this measure term. And then you're going to get 1 over square root of n. And this h bar and then we left just with m over 2 and h bar epsilon time the initial point, the final point minus the initial point squared. Okay, so now we left with, we can maybe simplify a bit this factor here, because then we want to take the limit. N goes to infinity, so let's see where we have this n factor. So here we end up with, if you look at this, and here it's n minus 1 to the divided by 2. Here it's n divided by 2, so we just left with m divided by 2 1/2, and then the exponential with the n coefficient, sorry. And the exponential is just the same. X prime squared divided by 2 h bar and epsilon. So then, how do I take this limit? What is n epsilon here?
The interval of time.
Yeah, okay, because you remember, so I divided my interval tau prime prime minus tau prime into n subinterval of time duration epsilon. Okay, so n epsilon is just what I'm going to call big T here, which is, so in fact, this is independent of, and in fact, so you just case in this free case that K is indeed equal to M as expected. Okay, if now you compare what we had here and here, we get the same thing. So just maybe one remark here. So you see that now if you, so this, the action here up to the factor h minus 1, it can be written as, so let's write it maybe. Times t, okay? And so this is just, so up to this factor, of course, and this is just the action of a particle moving along the classical path, okay? And for free particles, the classical path is, of course, a straight line, okay, as you can see. So here, indeed, this can be really, in fact, rewritten as something, so you keep this factor, and then you get this, so sorry about that, this one. So here, just what I want to say is that you have this term. which is times 2, which is the action for a particle moving on a straight line. So it's a classical action. Along a straight line. And this is something quite general that you're going to see. Where here it's xc for c classical, meaning it's a classical path. So what is very general, what is a general feature is that a path integral can be decomposed into 2 factors, and one of the factors is the this phase where you have the action evaluated at the classical on the classical motion. Okay, so this is quite general. So another classical general feature that maybe, so we haven't done in detail all the steps, but you're going to do them in the tutorial, is that typically all the calculation you're going to do in the integral formalism are going to be much lengthy and than using the standard techniques of quantum mechanics. Okay, so in quantum mechanics, why we are really introducing the path integral is just because we can already see many of the techniques that are going to be used for QFT, and maybe when we go to the perturbative theory, then it's become interesting. But usually we see that this calculation we did it in this framework, and it's in fact much easier than to compute all this Gaussian and this kind of thing. Okay. So any question here? Okay, so if there is no question, I have 15 minutes, which is very short, to talk about the second part, the semi-classical expansion, not really approximation. And so the idea is that we have seen that it's going to be always, so this is quite general, okay, that your path integral is going to be this factor where you have the weight is given by your action evaluated at on the classical path times another factor. And so let's look now at the semi-classical expansion, where we're going to expand everything around this classical path, okay, and see what we can say. And then we're going to use that, you're going to use that with your mark this weekend. So are you all familiar with functional derivatives? Perfect. Well, in fact, yeah, we're not going to use, the one we're going to do are quite similar to the normal derivative, maybe except one aspect is different, but I'm going to give it to you right now. So let's look at the second part, semi-classical expansion. And so I won't have time to finish, but I just want to introduce it because I want you to think about it maybe, or use it, apply it during the weekend. So let's consider this Euclidean action. And in fact, this is going to give us kind of a tool to compute path integral without going back to this expression in terms of the limit all the time. So let's look at it. So now to do the path integral, let's suppose that we know the classical solution, that I'm going to denote x of c of tau, that has this classical solution satisfies this boundary condition. Okay, so at tau prime prime, I want that this is x prime prime. And so by definition, of course, this is the solution of this equation. Okay. evaluated at xc. So we see that when h bar is going to go to 0, then all the contributing paths are going to be the one very close to the classical trajectory. So to do that, let's consider a trajectory of the type so the classical contribution plus some fluctuation, where here I even introduce. And that has, of course, we want that all these paths satisfy this boundary condition because it's the path contributing to my path integral, if you remember the definition. So here this means that my fluctuation are going to be taken equal to 0 at the boundary. So now let's look at the action for the path, for this path, okay? So we can now decompose the action as a power series, okay? So let's multiply this action by h bar. So my first contribution is going to be the classical path, and then I will have my correction, okay? So plus 1 over h bar x of tau, and this evaluating at x equal xc d2. So this is my first term, and I'm going to go, of course, if we evaluate x at xc, this term is going to vanish. So let's go to the next, and I want to go not only to the next order, but the next two orders, just because then you're going to see where the kinematical term is going to contribute to which order, and to which order then the potential is going to contribute. That it's so then I have the first order term, which is T2, and usually it's the one you will have to compute. For example, x of T1, and again then it's going to be evaluated at x, and I want to go to the next order, which is in square root of h. So where we get here u and we're going to see that this contribution only comes from the potential. Okay, so for example, in the case of a harmonic oscillator where you have a quadratic potential, then you're not going to see any correction. Evaluated again at x is equal to xc. And then, yeah, I'm going to stop my expansion here. Yeah?
How do you get the 1 over root h?
Okay, so it's, so I'm, oh, sorry, here.
Oh.
Now, is that clear? Yeah, yes, it's much clearer. Sorry. Thanks. Because yeah, of course, it's the term that appear in the path integral. Okay, it's not multiplied by h, but it's h minus 1. So that's the one I'm interested there. Okay, so you're all familiar with some functional derivatives. I'm going to give you maybe I'm not going to prove it here, but the only thing that is not obvious from, because even if you don't know anything about functional derivative, all the calculation we're going to do, you could almost use normal derivative technique. The only term that is tricky is this one. And I let you prove it. So where is that? So now I'm going to compute explicitly what are all these terms, okay, in the case where we start with an action given by that, classical action given by that, okay? And in fact, the only thing, non-trivial, and I'm going to ask you, it's one question of the homework for this weekend, guys, is to prove that is equal to, no, I have a derivative. Okay, so this is the homework 1. Yeah, I don't really know what I have time to do in minutes. But okay, I'm just going to give you the way. So here, to start with the action, I'm going to first do an integration by part, and this is a kind of trick that is often done when we have it's a way to find. Okay, so this is doing an integration by part. Okay, so it's exactly the same, it's just I perform a first integration by part here. And so now, of course, if I want to compute the functional derivative of the first one, okay, the first order here. So you know that, of course, so you know what it's going to give you, okay? You know that it's going to be the equation of motion, that for x is equal xc is going to vanish, but you also have boundary term, okay? And since we're going to the second order, we need to keep the boundary term to perform this second derivative and then the third one, etc. Okay? So I just don't have only the equation of motion. So here, what is the result? So if I do now compute this, you can show. So let me give you the result and maybe explain where each term comes from, and then I will let you check this. So this is, sorry, x of O. And then the term that you're expecting, which gives you the classical okay, so here now, if you want to find the equation of motion, you just, okay, this, which is And since delta Q is 0 at the boundary, because of the delta, it's going to vanish, and you end up with, so this is 0, it's equivalent to have your equation of motion, okay? So I'll let you convince you. And it's the Euclidean case, so it's up to a sign. But so where does this term come from, okay? So if you evaluate this in tau second minus tau prime, then you're going to get, when you look at this first term, it's going to give you, so because of this term, you're going to get this delta, okay, with the derivative of dx over d tau, okay? Then, as I remind you, you have this expression here. So normally, you should get also a term with the derivative of the delta coming from the fact that you have this term, okay? But in fact, if you do that carefully, if you look now at this, if you do the functional derivative of this term, you're going to see that this derivative of delta are going to be compensated from term coming from here, okay? So I'll let you check that explicitly. And then, of course, this other term comes from here, and this one comes from here, okay? So I let you check that explicitly, that you recover this result. And then we can go to the next order. And in fact, what is going to be important is that the boundary term here are always going to be a function of delta, okay? So this means that of delta with, in the delta, the tau prime prime or the tau prime. So when you're going to plug them into this equation, because of you have the fluctuation here that vanish at tau prime prime or tau prime, usually you won't see them, okay? And yeah, I'm sorry, I'm just hesitating in the way because I don't want to keep you so longer than necessary. So maybe I can just give you the final result, and you understood that you need to go term by term to get that. So I'm just going to give you what is the final result here, and then maybe you can try to apply that. One of the questions of the homework is going to apply this formula, this explicit formula, in the case of the harmonic oscillator or the free particle, and you're going to maybe see exactly what this means. But you're also welcome to check going from here to the second derivative and the third derivative, and why the boundary term are going to finally disappear at the end, okay? So let me just give you the result, and then don't hesitate to write in your homework question about the question if you want more detail about that, or if it's okay, anything you need. I'm just going to now. So then we can simplify. So we're going to get that the minus and I'm going to, anyway, in the lecture note you have not completely all the detail, but you have the. So here we're going to have. So the first contribution vanish, and the one you're left is something like this, where we're going to consider this object as a kind of matrix with continuum indices, where we will have to anyway evaluate it at the classical, on the classical path. And then, so what is important here is that at the next order, so I'm going to explain, give you what is this object. What is important here is only the potential is contributing. There is no contribution for the kinematical term, okay? And that, of course, it's only a contribution if you have some cubic terms or more. And so before expanding what is the A, in fact, this can be so now if we use the expression of And maybe I will come back on this step. So if now we look at just K, the propagator, you're going to see that you can write it as, again, a factor which is proportional to the weight is given by this action evaluated on the classical path, and then you're going to get some contribution of due to fluctuation of order h, square root of h bar. Where here you get something like this. And this expression can be used then to compute some of the path integral, which are otherwise quite complicated, because you're going to see that the idea is just to find then kind of, so this can be seen as a matrix with continuum indices, and the idea is that if you can diagonalize this matrix or maybe find the eigenvalue of this matrix, then you can compute explicitly this term, okay? Then you will have additional contribution, correction, and plus then. Okay, so here, the last thing I need to give you is what is this matrix with continuous indices, and just doing finishing the calculation I've started, meaning computing all these three derivatives, then you can show that indeed what you get here is just this kind of operator. The second derivative with respect of x of the potential with a delta. Okay, and so really now, if you want to apply this to any system, the main work is, of course, to compute this, evaluated at the classical path, on the classical path. And then to compute this, the idea is really to solve first the kind of the eigenvalue of A, okay? And I'm going to come back on that maybe on Monday, or explain that in the homework question, and then we can discuss more in detail. Sorry for being so late.